Thank you, and I'm very glad to be back here. Let me start with a remarkably simple idea from the mid-30s of last century. It is due to Krylov-Bogolubov, and here it is. You have a compact space and a continuous map and you want to study the long-term behavior of orbits under that map. So Krylov-Bogolubov idea is this. You consider these averages of Dirac masses on the orbit. And what they say is that since set of probability measures is compact, then you have limit points here to some measures. You extract subsequences and you have measures, probability measures. They are necessary probability measures. And these measures are invariant. So you can start doing ergodic theory with this. And let me emphasize that independently of dynamics, measure theory exists. You have a lot of structure in measure theory that you use all the time. As you know, the origin of dynamical system is rather to study differential equations. And in this talk, I'm mostly going to give the dictionary between this idea and what happens when you want to study foliation. This means differential equations in the complex domain. Especially when you are in the complex domain. So the type of problem we are going to consider is the following. You have M omega compact Kähler manifold of dimension k, and you have a maps, holomorphic map from a disk to M. The disk could be C or an arbitrary Riemann surface, but I'm going to focus on that case because it's the most interesting in my opinion. And you want to understand how this image distributes. That means you can imagine that phi, leaf of a foliation, parameterize a leaf of a foliation, or a stable manifold for a map, or just a family of disks. And we all meet a lot of families of disks when we work in complex dynamics. And you want to understand the behavior. What are the tools? Let me just say one thing. The time in the idea above is n. It goes to infinity. So we need a notion of time in some sense, though it's going to be given by this disk or Riemann surface. There is an interesting way to measure the growth of maps, and it comes from the Valina theory. When you have a map like this, the Alford-Shimizu characteristic, I will write that most of the time, TR, is a way to measure the growth of the map This is an average growth of the map. It is also the same as phi star log plus, use Fubini theorem and you get this, omega. The next point is what is the analog of these Birkhoff averages I have there. And here it is. TR phi is 1 over TR dt over t phi star of dt. This is the disk of radius t. That means you have an image here and you look at the current defined by the image of the disk of radius t, and you take this funny average. If I have time, I will explain why you have to take this average. Maybe let me emphasize what is this. This is 1 over TR phi star of log plus R over zeta, the direct image of that current on the unit disk. To be more explicit, I consider this as a current of bidimension 1, 1, positive. It's like if I were telling I consider a measure. How does it act on forms? Take a 1, 1 form, psi, then it acts on forms in the following way: 1 over TR, 0R, dt over t, dt, phi star of psi. And since I have divided by TR, I have that TR phi of omega is 1. So I have a family of currents of bidimension 1, 1, all of them of mass 1. It's like probability measure. You have compactness result, and you can take limits, like in the blackboard up there. You can take limits. So you have cluster points. What is the replacement of the invariance there? If you think of the proof of that, it's crucial to prove invariance that n goes to infinity. So here also we need TR goes to infinity. Assume, we have to check that in application. Assume TR goes to infinity when R goes to capital R, which could be infinite or 1 if we are in the disk. then you get something remarkable. You get that DDC, you can compute anyway DDC of tau r phi. This is a simple application of Jensen's formula, and it is phi star of the Lebesgue measure on the circle of radius r minus the Dirac mass at phi 0. Then the fact that this is of bounded measure, if TR goes to 1, to infinity, then you get DDC to infinity is 0. So you got a current, capital T, so that DDCT is 0. The analog of measure theory in the context of foliation, or more generally dynamical system in a complex domain, is the class of current T by dimension 1, 1, and DDCT is 0. They are in some sense unavoidable. Like if you want to do ergodic theory for dynamical systems, you need measure theory. If you want to do ergodic theory for foliations, you need this type of currents. You get actually something very big. What is the idea you should have in mind for this current? They don't, if you have C2 or Cn, there is no such object living in Cn compactly supported. Okay? So I claim that because sometimes some people ask me why your limits are not just a point. They are not a point because they have a cohomology class. T is necessarily a big object. It's like a complex curve in the projective space. It cannot sit in a small chart. That's very important. So we get always something that has a lot of structure.
So are you using that T omega is 1?
I certainly use that T omega is not 0. Okay, so for the moment I'm pretty abstract, but I just want to emphasize that if you have a sequence of disks, coming from your dynamical problem and you don't know what to do with it, you want to understand how it distributes, then the first thing to do is to introduce the current tau n, as I said, compute whether their T phi n 1 goes to infinity, and then build this positive dd bar closed current, which give you a lot of the structure of your family of maps. So this current, if you are in a complex compact manifold of dimension k, it's a form of by degree k minus 1, k minus 1, and the coefficients are measures. But it's very important to think of it as a current, because when you have a current, you are tempted to use the formalism of differential form, even if it's not smooth, etc. You have some temptation you should try to follow. Let me give you another very elementary abstract result. Here is the connection with this current with foliation. Take m omega compact Kähler assume you are given a family, arbitrary number of continuous 1-0 form, not necessarily holomorphic. Assume for every z, this is different from 0. So at each point, you have a direction. Then there is T positive by dimension 1, 1, DD bar closed, and T wedge alpha j is 0. That means T is directed by the kernel of the alpha j. I told that to one of my colleagues at Orsay. He's a very good expert in number theory, but since he deals with foliation, he knows what are DD bar closed currents. So he thought of it a couple of minutes and said, if it is that general, it must be very easy. He was right. It's very easy, and you can consider that as an exercise. I can give a hint. Use Hahn-Banach in Sullivan style plus maximum principle. So you always have a lot of these guys. For example, if you have a foliation given by forms, this can be local forms. You can just multiply by cutoff functions, and you get a current directed by these forms for free. And this current is the analog of invariant measures if you want to study the dynamics of foliations. So let me now turn to some more concrete applications of this. Consider a Kähler manifold, and let's be given a foliation f, leaves are of dimension 1, and then it's given by a family of holomorphic 1 forms, omega j, and the Gij don't vanish, they are holomorphic. And actually in my applications I will concentrate most of the time on surfaces. M is a surface. So you can think just of the projective space, then the foliations are given by a meromorphic vector field. So locally, the foliation looks like this in appropriate coordinates. And when you look at C3 minus 0, the projection on P2, then you get that P star of the foliation is associated to a holomorphic vector field Pj d over dzj in C3, and the Pj are holomorphic polynomials, homogeneous, all of the same degree, d. In P2, all foliations have singularities. That means at some point you have an expression like this, lambda w dz minus z dw plus higher order term. And when imaginary of lambda, I'm assuming here that I'm at 0 in some chart. If you assume imaginary of lambda is different from 0, then you say that the singularity is hyperbolic. Then there is a theorem of Poincaré, which says that if the singularity is hyperbolic, then you can find coordinates where your form is linearizable. That means you suppress these higher order terms. So you have a very concrete description of the leaves. Let me write a parametrization near the origin. They are like this. And they cluster on the two axes. If you remove the two axes, then the leaves are closed. So, in what follows, when I speak about foliations, I will restrict to the generic case where all singularities are hyperbolic. This is generic, and this is what I'm after. If I want to apply some of the ideas I discussed before, then I need to say something about the leaves of a foliation. Let me mention a nice result that in P2 and in higher dimension also, it's by Linz-Netto and Glutzuk, and they say that if this, in that very generic case, let me not be too precise, if the singularities are non-degenerate, then the leaves are parametrized by unit disk. That means the universal covering is the unit disk. There are stronger results, but I'm not going to mention that here. There is a remarkable result about the behavior of leaves, which is due to the Russian school, I believe in the 60s, Hudayverenov, Ilyashenko, and they say this: look at a foliation of P2, assume the line at infinity is invariant. You have a number of singularities here on the line at infinity. And assume all singularities are hyperbolic, plus some generic condition. Then all leaves are dense, except for the line at infinity. Quite remarkable result, very, not too difficult actually. And this is the first thing I want to discuss. If I want to apply the tools I have tried to sketch before, I need, the condition is still somewhere TR goes to infinity there. This is a result by Fournes and me, 2005. M compact Kähler manifold, any dimension, you have a foliation by Riemann surfaces. Assume for simplicity singularities are isolated. Let phi the universal covering for a leaf. Then TR phi goes to infinity when R goes to 1. The proof is dynamical. You have to evaluate how much time you spend near singularity. By now, there is a more geometric proof that you can find in my last article with Dinh. It just deals with singularities of currents. So it forces the mass to go to infinity. So we can take that for granted. I need something to erase. Oh, sorry. Here is the theorem. I state the simplest non-trivial form. It's valid in Kähler surfaces, but for simplicity, I just consider P2. And I consider a foliation. All singularities are hyperbolic. And I consider, I assume there is an invariant compact curve, but for simplicity, I just assume L infinity is invariant. Maybe a family of compact curve. Then, all the currents directed by the foliation are supported assume always singularities are hyperbolic, as I always, singularities hyperbolic, are supported on the union of the curves. So in the case L infinity is a unique invariant curve, like in Houday-Vereenhoff case, then L infinity is the unique DD bar closed current of mass 1 directed by the foliation. This is somehow a slightly surprising theorem, because in view of what the Houday-Vereenhoff theorem, he tells you leaves are genuinely dense. So you must expect that they distribute equally on the phase space. And here what we say is that indeed they don't. Most of their hyperbolic time they spend near the line at infinity. So there are in dynamics various ways of being dense, and this way is a little special. One can call that the Poincaré set. You have leaves parameterized by the unit disk. You look at this type of Birkhoff sums, TR phi, on a leaf, and you take the limits. They could be very big space. And indeed, the claim of the theorem is that there is only one limit, is the current of integration on the line at infinity. I think I will have time to say something about the proof, but let me just say that it's somehow a new tool which we call the density of currents. It's a way to analyze how much mass the current has near a curve in any dimension. Yeah.
So the assumptions are that L infinity is the unique invariant curve and all the singularities are hyperbolic. Is that it?
Yeah.
Nothing.
No. Yeah. But it's more general than that. You can just take many curves. All singularities are hyperbolic. And then the only thing you can say is that all the currents are supported on the curves. But you don't know how they distribute among the curves. Let me give a second theorem before going to the proof, and the second theorem is somehow the motivation of this talk because it's more recent. Here it is. Dinh, Nguyen, myself, and it says this. M omega compact Kähler surface. F foliation hyperbolic singularities, only hyperbolic singularities. Assume this is an assumption for convenience because we know very well to describe what is happening when this assumption doesn't hold. Assume no positive directed closed current. This is the most interesting case. I said it. For example, if you are in the projective space, this means just you have no compact curve. That's all. So it's just the complement of the previous theorem. Then there is a unique T of mass 1 by dimension 1, 1, directed by the foliation. It means, I hope everybody understands, T wedge omega j is 0, and DDC closed. It means that, in particular, that if you look at a parametrization of a leaf by universal covering map, it means that this TR phi converges to T. This is a unique ergodicity result. You say that averages converge to T. But I want to emphasize one point, because the universal covering map doesn't play a special role. You just can use any map with the Alfors Shimizu characteristic going to infinity. For example, you can take the universal covering map given by the unit disk and just reparameterize to take in just by this small region here. Then you can compute easily that TR phi goes to infinity, and then you have always, you converge to the same limit, which is maybe interesting for dynamically oriented audience, because we are used to finding the same picture at different scales. And this is what it says. You can change the scale, you are not going to change much of the distribution of the regions you are looking at. Okay. The last result I want to mention, just to tell you that this is not limited to study of foliations. The technology which is behind this theorem, as I told you, we call that density of currents, and it permits to study also problems like you have an algebraic variety, and you have maps there. It could be an automorphism or even birational maps. And you want to study the distribution of periodic points. it's basically the same technology. Because what you want to know is how do the graphs behave near the diagonal. This is typically a problem of density of currents. And since many people here are interested in Henon maps, let me also mention this result. And revisited by Dinh and myself, you have F, a Henon map in C2, Henon type map. You know what is K plus, the set of points with bounded orbit. There is a unique positive DDC closed current supported by K plus of mass 1. And it turns out that this current is closed. It is the limit of what, limit 1. If the Henon map is of degree D. So it tells you that if you have a large disk, meaning the alpha-Shimizu characteristic on K plus, you try to average, you get always the same thing. Okay, so, hopefully, unfortunately, I don't have much time, but I can still sketch the proof, sketch one proof. I'm going to sketch the proof of this theorem here. So you have the line at infinity here, and you want to prove it's the unique DD bar closed current directed by the foliation. Then take a current T, no mass on infinity, no mass on L infinity. And you want to prove T is 0 and DDC closed and directed by the foliation. Then there is a part that has not much to do with dynamics or foliation. It's just the part corresponding to measure theory. You study DD bar closed current, positive. And in this simple case, you just make dilatations of the current T. Lambda is going to go to infinity, just somehow to look at what happens with a microscope near the line at infinity. Dilatations start here, and they correspond in this case to the normal bundle. You make dilatations on the normal bundle. And then you prove that there are limits, S, when lambda goes to infinity. The limit is not unique, but if P is the projection on the line at infinity, S are going to be the pullback of some measures on the line at infinity. And the important point, the basis of the calculus in this case, is that the mass of the measure nu is the class of T cup product with the class of L infinity. This is an interesting formula because it tells you, since we are in P2, that if I want to prove that T is 0, it's enough to prove that the class of T is 0, since it's positive. A good point also is that DD bar closed current have a class. And to prove that this is 0, it's enough to prove that nu is 0. Then we are back in the context of foliation. We want to prove that for a foliation, nu is 0. If I am away from singularities, it's more or less trivial and it's an exercise. Because you can write T as an integral of harmonic functions d mu alpha, and mu has no Dirac mass on L infinity, and just uniformity gives you the result. The delicate point is when you are at singularities. Then you have to deal with the behavior of these harmonic functions near singularities, compute Poisson transforms, etc., and do some substantial technical work. I have a couple of minutes to deal with the theorem which is there, which took us a lot of time to write down. And basically, it has to do with, on one side, pluripotential theory. Pluripotential theory, by this I mean study of DD bar closed current. A priori, no connection with the foliation. And the second step is apply this to foliation. The study of DD bar closed current was started long ago with Fournes, and basically when you have a positive DD bar closed current on a Kähler surface, you can write it in this way. This is just by playing with the Hodge theory. S, ds, d bar s are all in L2. And we needed an improvement, which, and you, in the work with Fournes, I guess, was in L2. We needed here a very important information, is that du is in LP for p less than 2. So you prove a priori a regularity theorem for positive DD bar closed currents. And with this at hand, you can consider the manifold M cross M and the diagonal delta in M cross M. And when you want to study a current, T, which is positive DD bar closed on M, what you do is you tensor it with itself. Now it's not anymore DD bar closed. But you make dilatations, you change space, you are in the normal bundle, and you prove that all the limits will satisfy a nice formula. Somehow the corresponding to nu there is be omega square minus d bar s ds bar. And it turns out that this regularity result plays an important role. And then, with the same strategy, you want to prove that nu is 0, and then using some Hodge theory, like here, this type of algebraic geometry, you end up getting the uniqueness. So I'm just, as Xavier reminded me, I'm just finished, so thank you.